he before walking to Manipur University, before walking here, he was in PRL, Physical Research Laboratory, as a scientist. Then after he joined here, then so many achievements for him. So let me name a few, because if I name all these things, this will take a lot of time. Right now, currently he's a member of Scientific Advisory Council, Center for Atomic, Molecular and Optical Science and Technologies, joined initially by IIT Tirupati and ISER Tirupati, and also a member Board of Studies of Physics, Indian Institute of Teacher Education, Gandhinagar, and associate member for Center for Computation Science, Material Science, Jawaharlal Nehru Center for Advanced Scientific Research. So let me name a few. So now let us welcome Professor Dilip Kumar Singh for his lecture talk.
Okay, so good morning to one and all, and I thank the organizers for giving me this opportunity to present some of the work that we have done. However, what I'll try to do is I'll try to give a very basic outline, not go into the technical details, and you please feel free to interrupt me at any point of time. So the title is Quantum Phase Transitions, and now the quantum phase transitions is associated with the quantum system. However, the idea or the concept of phase transitions, as you all must be aware, is ubiquitous. The phase transitions. The Kang is the thermal phase transitions. What does it mean? Thermal phase transition have the that is water boiling and getting converted into vapor is a thermal phase transition. And it happens because you apply energy by heating it up, and the phase of the matter changes. And that we are very familiar. Okay, human beings are a phase transition. We are going to be a Komari Pali. Sanjara Charlie. They call it a Kongani. Kongani Taraga, upright, we walk upright. They call it a Kongo Pali. So, this is also some sort of a phase transition that we encounter in our life. Now, the plan of presentation is, it will be introduction, quantum phase transitions. Then, in the past, for nearly a decade, I have been working on this system, that is optical lattices. So, I'll just give you a very brief outline of such a system. So, the introduction. Now, you must be familiar with the phases of water. Phases of water that we are familiar with consist of this part is vapor, this part is liquid, and this part is solid. And this is what is referred to as the critical point. The critical point is the end point of the phase difference or the phase separation of the liquid and gas. So, what can happen is that, so this is the temperature, this is the pressure. So, we can go along a path that takes us from here to here. That is by changing temperature and pressure. So, the critical point is the point where the two phases coexist. However, the very essence of life that we know of, because without water there cannot be life on this planet. And these are the three phases that we are very familiar with. However, if you really look into the details of the phases of H2O, water, then it looks like this. And I am sure none of you may not have seen this kind of a phase or the phases of water. As I see never the saying ising phase diagram haragadi. Akoina kang is the ising manil, ising adagi un. These are only three phases that we are familiar with. But if you look in more details, if you change the temperature, so there are so many phases of water that can exist in nature. So it can be at the core of the earth, it can be at very extreme pressures and so on. So why are we interested in phase transitions? As I was telling you, phase transitions are everywhere around us. Now, how do we identify phase transition? Normally, in our understanding that we had learned in thermodynamics, we learned about phase transitions based on the free energy and its derivatives. It is first order if the first order derivative is discontinuous, and it's of higher order if the higher order derivatives are discontinuous. However, in the modern times, in our understanding of the phase transitions, first order we refer to as the first order, but the other higher orders we call it as continuous. Hadi haujikangi language that kari hagi matlab first order is the first order and the high, aduga second order, third order and akwen high. The physics ki terminology degi was a continuous phase transition and the high. See maram di kari gena matlab the first order is the magi latent heat with the lake. Aduga second order and higher order is the latent heat late. Adu latent heat like the giving a side continuous phase transition high ki maram di kari gena have matam da magi da ngasai gi akhoi thermal phase transition seems the temperature change the matam da ngasai gi magi phase change the aduna sorry continuous phase transition have ki maram di around the phase transitions there are properties of the system that diverges. An example is the correlation. Hadi akoina ising when leram badagi ice when a pull up when on gives come I to own green. Hadi amukta the pull up to ngasagi then go to the yard ising the amukta the pull up ice one gadra. Nadraga macha the git or own gidra. Sigma phase transition je. See matang the name was okina kariko get the criticality critical phase transitions and critical phenomena. At the height of a phenomena they apply to Vayaki have second order and higher order phase transitions. Other criticality having a infinite or magi property may infinite or adugidubu okoina criticality and continuous phase transitions. This is what is interesting from our perspective. Normally thermal phase transitions. Phase transition is to create the Korean Kangri have matamda. Nasagi ising na man ice on great already. Ice to the crystalline or patam. Crystal or the crystal properties. What is the property of the crystal that defines its phase? Then it's a lattice constant. So, like that, there are properties of a phase that identifies that the matter is in that particular phase. And that property is called the order parameter of that phase. So before we understand what is a phase transition, what is important is to ask the question, what defines that phase? Phase amadagi phase amada hongre have is si khangi hai tar gadi akoina yamna maru ba marula si karina matamda akoina thengnare ba anoba phase dugi magi defining character magi madu masak tak pangamba magi magun ma kwen thi dakar ta I know the ising the gi karigumba I say one give target is the crystalline crystal gi karino magi property as a lattice constant. The mind of Sagi Aquina Sugumasibu Kaiko order parameter kawi. I zoom among the high Sagi change in temperature drives the phase transition of liquid water to water vapor and Bose-Einstein condensation. See Matang Ina Masai and Obama introduced our Bose-Einstein condensation. A quick example of sorry. A Ising model. My Ising model can be Ramani, Technobi Ramani. Statistical mechanics that Yamna Marueba model Ramani, the spin mayam labor, Magic crystalline and a Magi Karuma order Ramada. At a high Ribanga Sagi, Ising model Ziggy phase transition G, two types. I'm an ordered phase. This is ordered phase. Kawi. Ordered phase is the Sagi magnetic moment pe am je loin pull up align tong ne in a direction, and hence it has a magnetic moment, a finite magnetic moment. Adi atopa mana ngasagi disordered. Disordered sina kind of ngasagi magnetic moment le spin mai me am je loin misaligned to by tar. Adana sigi zina loin in random direction oi benina magi magnetic moment is zero oi. Sig is not a classical perspective. Classical perspective the karino sig is na ordered, sig is na disordered. Adu akone quantum mechanics te targadi akone field theory gi yeng targadi amukari hagada geda this is symmetric. Hadi sig is a maikai khuding maktagi yeng mo tam sidi chapmanani. This is non-symmetric. Haibagi artadi akone siguma system amazi yeng mo tam da sondagi yenge chapmanani sondagi yenge chapmani sondagi yenge chapmanani maikai khuding mate lai chapmanani. This is symmetric. Whereas in this case symmetry is there, it is broken. Habiga tri akone sondagi yeng mo tam de solo loin tore sondali yeng mo pai le adna sigi jide symmetric oi drive. Adna ai haibagi artadi akone spin system ji yeng mo tam da we can look at it from two angles. One from the classical, IDC spin noise classical treatment of VI. Madu gidana sig ordered way, sig is disordered way. Quantum mechanically, amu yang targade. I is sleeping mode after. Sig is symmetric, symmetric because you look at it from any angle, it will have the similar structure. This has broken symmetry. Habiga this is symmetry do. Sidadi madu tugai grave. Adana Mike Yama the Yang Baga, Autopo Mike the Yang Baga, sees a Kerkenova layer. Okay. So this brings us to the concept of Yamnamaru concept. Sidagi, see the transition to Akuna Kariko, spontaneous symmetry breaking. Adana Akuna quantum mechanics, the quantum physics, the Laknotam the Dikari Hagematamda. It involves a spontaneous symmetry break. Adana akoi na ujik lazy sig is a paramagnetic oideni sig is na ferromagnetic oiden spin systems ta adana masi kamai to gerege amatamda sidagi transition son the transition to be abasi akoi na temperature si sai Curie point to found is matamda maji amat thoni adige to pa mana external magnetic field salung apply matam maji da thong son the muk to gen amata na sai phase transition je makalani mata thon be one that is driven essentially by the temperature that reduces the fluctuations in the system, that is orientation of the spin. The other is the forced transition that is exhibited by the system in presence of an external field. So, I thought I phase transition, makal ki situation, I thing. Adana I know I give though. Nasagi phase transition, na gupumatam, Aquina, tenko amada ising tambazi, ising zina. I soon give the unwon give a mature roll pra. Not until pull up on here. High begi wahang si akwen kumbamatamda, kari darkata gimatamda. Critical temperature magi properties ya. Kamain to give. Hadi akwena yamna physics the marueba idea ma lay, but the correlation. Correlation with the akwen portam logotamda. Sidale jagas magi property to go, autopum from the labor property to uneasy kari marine again. Other sugar correlations in a sagi phase transitions in Naxilla correlations infinite work it will diverse. Other kind of A have a properties it will diverse with respect to this reduced distance with a negative exponent. Other than Sigis when a Kangbi of the Kariko game with them, the Sigi exponent in there was a critical exponent cover. And when the Sai has a give though. First order transition, it is there, it has latent hit. Second order and higher orders. Second and higher orders, is a continuation recovery, a critical phenomenon. Critical recovery, Sigi exponents. It is critical. I think say diverse over here. Other than say, here properties. For example, if you take the case of a correlation length, it will diverse. High big artadi. The say, I think what the lower ising duna, ice one but unknown by say, Mafom is olakani, Mafom is olakani, among the pull up the olum the bayat, to the property says the it is across the system. And I think one swimming pool lowering color. When temperature some the swimming pool corner amaga atopa corner amaga property and easy. Have it adu manner can you? I don't know phase transition is it over second and higher order day. Say critical exponent is a CG the Qatar. aduna critical exponent gi importance karine ba tamda ngasai gi isingna un ba adagi akhoi gi magnet na ferromagnet on ba siguma mayam se sigi matang sida kari toge matamda same physics edi ngasai gi isingna un on beda changi ba magi madu ta iba sigi critical exponent adagi ngasai gi paramagnet na ferromagnet on beda magi criticality adusu sumai to very diverse yam kena ba physics ki system me am je ngasai gi same exponent na maji masak tak pangame adu masigumba group of properties group of systems which are described by the same exponent is called to belong to a same universality class aduna habi adadi different systems magnetic systems ngasai gi criticality phase transitions is zero targadi ngasai gi my near the phase transition same property follow to kanya aduguma system am plug to pullaga moje universality class amai thole sigi jina loin classical concept laktani adana hojiki haije Ising model adi akhona brass je changing abo rangani changing ji akhoi gi alloy ni alloy gi jo mage jo phase transition edi karino tamda alloy ji akhoi gi kori ga atopa dhatu kharga pullaga sabani adu moi je hit to tamda ngasagi madu de yauri ba akhoi gi metals ke do elements ke do separate to thor ko yawi karim kanda temperature pressure ki method moi je mix to adu sigi jo phase transition maka siga ngasagi they belong to the same universality class adi spin system jiga sigi jiga moi ge phase transition ja chap mane other system yam kene they are so different but the physics behind their phase transition is the same so this is referred to as the critical phenomenon likewise so this is the system that we study optical lattices this is the spin system that's very popular so they have the same universality class aduna hojiki akoi chawakpa ma akoi gi phase transition is karino why they are interesting moje kari character lay kramain tor ga moje define to be je akoi chawakpa ma khangen na lobe yare adu akoi quantum phase transition da la ajeo aina hojik for the high given phase transition mayam ji moje thermal phase transition how you change the temperature and then you experience that the state of the matter changes from one form to the other so that is the driving force behind those phase transitions are essentially temperature is the control parameter and associated with temperature you have thermal fluctuations adi akoni statistical mechanics ta nene badai je temperature what is temperature it is the characteristic or corresponding to the characteristic distribution of the energy among the various particles ideal gas statistical mechanics definition adu akona quantum phase transition is the karino quantum phase transition the two fluctuations ka mari lainai but that fluctuation is not associated with the thermal but that fluctuation is associated with the quantum fluctuations now you can ask the question what is the origin or what is the genesis of these quantum fluctuations the genesis of the quantum fluctuations is that behind the quantum mechanics there is a very important principle that is Heisenberg's uncertainty principle so based on Heisenberg's uncertainty principle when you make a measurement or a system there can be some uncertainty in the canonically conjugate variables for example delta t and delta e so that leads to some fluctuations and now let's take the case that there are no thermal fluctuations like the Vedikaram Kandalaini it will be at absolute zero other absolute zero is it important is it achievable aduna pure quantum phase transition ji akhoina theoretically neneba matamda karam kanda thokadage matam zero temperature now from a theoretical perspective when can the quantum phase transitions occur it can occur at zero temperature when all the thermal fluctuations have ceased to exist in the system then what is prominent what becomes much more prominent are the quantum fluctuations and the quantum fluctuations are essentially associated with Heisenberg's uncertainty principles which is one of the building blocks of quantum mechanics now once you have that as you change the properties of the system that is in terms of a parameter of the system, what will happen is that the character of the quantum fluctuations will change, and associated with that, the system will exhibit a change in its state, and that is defined as a quantum phase transition. Now, one question that can arise here is that if the quantum phase transitions indeed occurs only at 0 temperature, then what is the importance of studying it? Because 0 temperature is not achievable. So we'll come to that. So for example, why uncertainty principle? Because if you take the case of an hydrogen atom, how is the electron distributed around the nucleus? So it will be a probability. So at one point of time, the electron could be here with some probability. If you make a measurement, it may be here. So that means there is a certain diffusion or diffuse electron position is there, and we can talk in terms of the probabilities. So the bit associated with probabilities will then be the fluctuations. Now, what does it mean? Quantum phase means in quantum mechanics, what is important is that the way how we are familiar with, we normally work with Hamiltonian. Now, let's consider a system that has the described by, which is described sorry, that is described by this Hamiltonian, that is consisting of two parts, H0 and H psi. Now, associated with H psi, there is a parameter G. So what is going to happen is that as we change G, that is parameter in the Hamiltonian, so the property of the system will change. Now, this is at 0 temperature, essentially quantum phases. Now, when it changes, so there is going to be a change in the property of the ground state. And earlier, what I had talked about is this criticality in terms of the reduced temperature, because in thermal phase transitions, the driving parameter is the temperature. Now, in the case of the quantum phase transition, the driving parameter is a parameter in the Hamiltonian, or a property of the system, let's put it, other than temperature. So what can it be? It can be the strength of the interaction. It can be, say for example, the distance between the atoms or distance between the molecules, and so on. So you change that and the state of the matter will change. These are all at 0 temperatures. Now, as of now, the study on the quantum phase transitions has become very important, and that is because so far you have heard a lot about quantum computers in different systems with different realizations. Now, in all of these quantum computers, the way to do a computation is that you have this unitary gates and you manipulate the state of the system. You start from some ground state, and then in order to do the quantum calculation by the quantum computer, what the quantum computer must undergo is some change in each state. Only then it can do the calculations. Now, that change in the state of the system means you are going to control it by some interaction or by changing some parameter. So what it means is that from the perspective of the quantum computers, what is also becoming very important is what are the phase transitions that it can occur. And the other important aspect is that, as you must be aware, in quantum mechanics, if you have a ground state, and if the system is not in the ground state, if it is in an excited state, it will always decay. So, in the case of quantum computers as well, it is essential to understand the phases of these quantum systems. So, this is why it is important, or rather it is becoming very important to understand the quantum phase transitions of these quantum systems. Okay, so I am almost halfway through. May I question later? I'm going to some question? Yeah. Yes.
Does this quantum phase transition occur only in the absolute zero, or you're mentioning it is driven by quantum fluctuations?
Right.
Quantum fluctuations invoke these quantum phase transitions at higher temperature as well?
Yes. So that's what I'll come. Okay, that's a very good question. So what it means is that so the pure quantum phase transitions will occur only at 0 temperature. That is, when only the quantum fluctuations exist in the system. But then, as I have been emphasizing, that is not achievable. So the important point is that now in the system, we have two fluctuations. One is the thermal fluctuation associated with temperature. And if we have a quantum system, we also now have quantum fluctuations, which will be the only fluctuation in the system which is at 0 temperature. But at finite temperatures, what is going to happen is that you'll have thermal fluctuations as well as quantum fluctuations. Now the question is, when is quantum phase transition important? The quantum phase transition in the system will become important when the quantum fluctuations dominate over the thermal fluctuations. And that can happen at finite temperatures. And that is why study of quantum phase transitions is so important. And in fact, for example, the high TC superconductors. The reason why it is so important to understand the physics of high TC superconductors is that so far we do not have a theory that explains high TC superconductors. And the other reason why it is sort of a mystery is that we cannot really understand the phase transition that occurs. Because it's again a phase transition. You have a material that is essentially an insulator, because high TC superconductors at normal temperatures are insulators. But then you keep on decreasing the temperature, and then suddenly something happens and it becomes a superconductor. And the theory of superconductor has to be based on quantum mechanics, because there is a need for couple pairing. So how does this transition occur? For the normal superconductors, the BCS theory explains it quite well. It's well understood. But for the case of the high TC superconductors, we know that there is a quantum phase transition that occurs, but the physics around this quantum phase transition, that's what people are trying to explain. And there are various theories. Each of those theories can explain one aspect, but not the other. Okay, so that is what is important. So novel quantum phases have applications in quantum devices. Then essential to understand quantum phases to make working quantum devices. Unsolved problems like high temperature superconductivity have connections with quantum phases and their transitions. Okay. So this is what I was telling you. So delta is the parameter associated with the quantum fluctuations. KBT is the thermal fluctuation. So when they are comparable, then it will be important. Kelvin ki question do na to atai ma'am. Aini sum chathagradhi asum sai da dum lepaga dum kamayam question hang birji ai kisu kai de. Ai hoji hai graji si bau yogra. Si quantum phase transitions khar changjile ai. Adagi quantum phase transition gi kari gi maru ori no haibiduma leire. Adagi akoina kasage phase transition da aina hajagiba criticality admai to na quantum phase transition so criticality lay criticality do ngasai gi keno dana thermal phase transitions dana akoi na ngasai gi with respect to temperature kai gi no the temperature to na driving force ba parameter ba aduga ngasai gi quantum phase transition dana ngasai gi change in the system Hamiltonian ngasai interparticle interaction obi ai aduna tragana magi magnetic field obi ai admai to da isagi smai to criticality ama laini aduga quantum phase transition ki maru obidi kari na ta akoina quantum computers kumba hojikani akoi gi hojikse second generation of electronic devices aita second generation of devices aduna akoina quantum mechanics it's not something abstract. We are all familiar with it in some sense or the other. Karigano tum mayam hoji okay medical sciences the MRI na mayam tabiramani. MRI ki basic principle di it is nuclear magnetic resonance NMR. I think asagi ortho ga pera ga hydrogen gi asagi magi resonance to ni. So quantum mechanics. And MRI gi su okay na ta saying na working principles ji khangi hai targa di classical mechanics ni yar quantum mechanics na little then. Adi matam sang na kuin de dam X-ray. Kamai taroga X-ray ji generate hobi. Okay, high energy electron beam mana metal amada yaira kanda X-ray ji thoi. Kari maram geno inner shell electrons to kicked out toraga madudagi decay to. Aduna akoina quantum mechanics si physics ki satra madadi to dogna strains hoide. Kaya na akoy badalo laire. Aduna quantum systems in these quantum systems as well we have these phase transitions. So this is the phase diagram of a quantum system that exhibits a quantum phase transition. So this is temperature, this is the system parameter. You change the system parameter, but at zero sorry, at zero temperature, as it reaches a critical value, it undergoes a phase transition, a change of state of the system. But normally what we have is temperature is finite. So the actual phase transition will have like this, and this domain where the quantum fluctuations is a little smaller than the thermal fluctuations. That is when the quantum fluctuations will play a very important role, and that is why this is called quantum critical. Sigi regions is the classical or thermal phase transitions. Sigi sidana koi to gebu ngasai temperature is the finite way to budabu magi quantum nature do adu neglect to biya sigi domain jida. Admai to ngasai gi akoi gi high tissue superconductor ki phase is phase diagram is my happy to we so is the ngasai gi blob amale. Other blob ki around that blob of the high tissue superconductor, the properties, how the property of the system changes, that is still a challenge. Other than quantum phase transition, see, Yamamutana Kambagi, the Karnia.
Small z is a very important parameter here.
Right. Yes, absolutely.
What does this z depend on for a system? Is it a constant number, or it has some dimensions, or what does it depend on?
Okay, so it can depend. Okay, so it can depend on the system. It's a parameter means. Say for example, okay. So let's take the case. So if you have a system that is electromagnetic system that is interacting with an external field, then it will be that external field. Okay, let's say that we have a quantum system, and that quantum system, if we can control it with an external field, then it will be that external field. Now, if you look at the Hamiltonian, what does it mean? If in the case of the electromagnetic theory, whenever we say an interaction term, it means a term that comprises of an electromagnetic moment like the dipole and an external electromagnetic field. If it is the electric dipole, then it will be electric field. If it is the magnetic dipole, then it will be magnetic field. And likewise, the higher moments will also couple to higher moments of the field. So in the Hamiltonian at zero temperature, if it is a dipole, then it will be d dot E. So d is an intrinsic parameter of the system. So that d you cannot change. So then the control parameter, the z equivalent of g will be the electric field. Now on the other hand, you can also have these optical lattices that I was talking about. There it can be the interaction or the tunneling. So if you have an array of quantum wells, so most of these quantum computers, essentially they are array of quantum systems or qubits which are coupled to each other. Now the coupling between these will essentially be determined by the separation. All these quantum systems are trapped in quantum wells. Now the idea is that the parameter in those systems would be, for example, the height of the barrier. Okay. So like that, there will be some parameter that you can change. So that will be this parameter g in the defining Hamiltonian of the quantum system. Does that answer your question? Okay. Do any other questions? Okay.
There is this notion of crossover, not the phase transition.
Yes, there is.
My question is, does crossover occurs only for finite system, or?
Okay, that's again a very important question. Now, so far I have not said what kind of a system or when does a phase transition occur. And the strict definition of the statistical mechanics, as I was telling you, it has discontinuities. Discontinuities means divergences, meaning there are infinities of the system. However, if you look at the statistical mechanics, any property of a statistical system is defined by the partition function. The partition function z is essentially a sum over e to the power minus beta e divided by sum over. Now, the sum over of these for a finite number of particles or a finite size system will always be finite. Is that okay? Because it's an exponent to the power minus, it's a negative. Exponent to the power minus is never 0, it will be however small it is, it will be a finite. And then when you sum over a finite number of finite quantities, you cannot get infinity. But the phase transition essentially requires that there will be discontinuities. Discontinuities implies infinities. So if you take a finite size system, in the strict statistical mechanics definition, there can be no phase transition. So that is why when you learn about statistical mechanics, you'll always learn about, what is that? Thermodynamic limit. The concept of thermodynamic limit is essentially required, it's very essential to explain some phenomena like phase transitions, because otherwise you cannot have any infinities in the system. Now the definition of the thermodynamic limit is that V tends to infinity, N tends to infinity, but N by V, that is the density, is finite. So that is the invoke. So to answer your question, Nilikas, in the strict sense of what the phase transition is, you need thermodynamic limit. However, it is now established that even finite size systems can exhibit phase transitions. That is why now there is an emerging field that's called as quantum thermodynamics, thermodynamics of finite size systems. And that is again very important because all these quantum devices, quantum computers, these are all finite size systems. But you want them to undergo phase transition, you want to manipulate these systems from one state to other so that we can exploit these for doing some calculations. And there you have to use this, So there is essential to understand if these systems can be described by what we have understood in terms of the statistical mechanics. So that is why there is this new field. And the crossover, yes, it's another type of a phase transition or higher order. Yeah. Does that answer your question? Or have I gone tangentially?
Actually, my question is, there has been some study of crossover. So
oh, yes, yes.
This crossover, they are in finite system or finite systems?
So that's what I was trying to answer. Normally, by in terms of the statistical mechanics, yes, whenever we say any phase transition, whether it's crossover or any order, it has to be in the thermodynamic limit. But in the case of the finite size systems also, we can have these phase transitions, and that will be defined in terms of this quantum thermodynamics. And now the crossover, that is often discussed in the case of the QCD, okay, QCD phase diagram. Now there it has to be in the thermodynamic limit. Is that okay? But in the case of the finite size systems, yes, there can be phase transitions, and then there is associated phase associated kinds of phase transition. But another topic that I have not bothered is that how this happens in the case of finite size systems. There is still an ongoing studies, the phase transitions, forgetting about first order, second order, or any time. So that's what. But yes, crossover does exist in the case of the thermodynamic limit. An example would be the QCD phase diagram, which is in the thermodynamic limit. So any other questions? Okay. So I think I have only 5 minutes, so I'll just quickly go through. So one of these quantum phase transitions that is very important is that it is in the context of the Bose-Einstein condensate. So the Bose-Einstein condensate was essentially predicted by Einstein based on the calculations of Bose, Satyendranath S. N. Bose. However, the actual observation of BEC, a truly BEC, a BEC state occurred only in 1995. Before the liquid helium, which is a superfluid phase of matter, sorry, we understand that the superfluid helium, for the superfluid helium to exist, there must be Bose-Einstein condensation. However, in the case of the superfluid helium, the fraction of the Bose-Einstein condensate that exists is just about 20%. Remaining 80% are just normal fluid. So that's why when we discuss about the superfluid, you must have come across this two fluid model, normal and the superfluid component. So it was not entirely 100% superfluid. It was only in 1995 that a truly Bose-Einstein condensate could be observed. That is almost 99.9 Bose-Einstein condensate. So with that, what has happened is that we can clearly have, so when we have this Bose-Einstein condensate, it is a macroscopic, really macroscopic in the sense that the size is of the orders of micrometers, and the system is completely coherent. It's an entirely quantum system. So this was a big achievement, and of course, those who managed to achieve this were awarded Nobel Prize. And so this is again a quantum matter, a truly quantum matter of macroscopic size. And if this Bose-Einstein condensate were to undergo a phase transition meaning from one possible state to another, then there would be truly a quantum phase transition. Okay, so that has led to a lot of discussions. So this is what it means. If it is a fermionic system, then when we have degeneracy essentially means ground state is macroscopically occupied, and the interparticle separation, that is the distance between these particles, are of the same order as the de Broglie wavelength. That is, at normal temperature, these are the particles, gas particles. Now we cannot really define its or the de Broglie wavelength of these particles will be of the same size as the particle itself. But you cool down the temperature, since the de Broglie wavelength is inversely proportional to the square root of the T, that is the temperature. So as you cool down the temperature, slowly the de Broglie wavelength will increase, and if you keep on decreasing it further, the de Broglie wavelength will keep on increasing, and at some point the de Broglie wavelength will be of the same size, or de Broglie wavelength will be of the same, will be similar to the size of the system. That is when the system of those bosons will undergo Bose-Einstein condensation, and it will be macroscopic. Now, the reason why it has not been observed for so long is that this occurs normally at nano Kelvin, that is 10 to the power minus 9 Kelvin, which is difficult to achieve. So that is one reason. So in the case of fermions, they will occupy up to Fermi energy. In the case of bosons, they will all try to occupy the ground state. So this is when the Bose-Einstein condensation will occur. And now these in gray are the ones, are the elements for which Bose-Einstein condensate has been observed. So there are many of these, and these are the, I think my time is almost over. So I'll just flash through the slides. So this is the phase transition. So there will be these divergences at these points. And now if you have this BEC, and then you shine this laser light from opposite directions to form a standing pattern, then you will have a potential which will trap these atoms, and experiments look like this. So essentially this is an optical table. These are various optical elements, and this is where these experiments are conducted. So essentially at this, inside this, what you will have is a Bose-Einstein condensate that is trapped in an egg-crate-like potential. There is an array of potential wells, and then you will have different quantum phase transitions that will occur. So this is the model Hamiltonian, so let me not go into that. So this is the phase diagram. So in my group, we have been looking at all these systems, and these are some of the works that we have done in recent times. It's not exhaustive; it's just a selected list. And then, so my collaborators are these, and these 4, they are my former students who are now faculty members at IITs and the Central University of Rajasthan. Then 3 of my former PhD students, they are doing postdocs abroad. 1 in Germany, 1 in Italy, 1 in US, and Deepak probably has gone to Delhi. So he's here with me, so he's sort of helping me establish a group here. And here I have some students who have started working on this. So Koenji, Lakshmi, Bhumika, and Momin. So there are 2 more, Bikramjit and Bandana. They have just started. They have not really looked at any specific system. So I think, let me wind up there. So I must also thank the funding agencies, that is ANRF, UGC, and Manipur University. These are the projects. So let me wind up here, and if you have any questions, so I will be very happy to answer. Sure. Feel free to ask. Question is hang biyo me any hang biyo kesu kai di.
What does that order and disorder phase transition really imply?
Okay. Okay. I did the order disorder hai che kai no ba matam da sinida. Akoina crystal hai ba matam da di akoina normally akoi ki kareta hai condensed matter or solid state physics ne na matam da di everything is uniform natra. It's like lattice constraint ne a hoita di cubic lattice ne lau ta ga di if you take an a lattice site at a distance of the one lattice constraint on all 3 directions, you will have a lattice point. Other tobudabu asengba crystal study kind of it's never ideal. Mage crystal defect lakani, adi impurity lakani. Natra. Aduna nasagi akogi crystalline habaga amorphous habaga aniji kari de khenari no. Hadi akona iron ji for example, iron yochi nasagi sahalaga saudohalaga tam inhaladi maje adum iron oina nasagi crystalline state tu oini aba. Aduna tebde nasagi yoche yam plana sahalaga kangai ingdan targadi magi nasagi crystal sembagi matam sangjabado adu fangringe da akoina magi temperature do yam makhata na inghan gitari maje crystal form to reba. Matam do maje kari organi da amorphous disordered phase ramne. Aduna akoi with the level tam the disorder phase yam some have the akoi glass disorder and maje supercool liquid ka jai the same way the supercool liquid it's a solid. Aduna supercool liquid si kamai to get maje it's not uniform maje disorder system. Aduna ngasagi disorder is the so ngasagi order to disorder phase transition je kamai thoke si ni da si matang jida naina baje akoina disorder system. The idealized systems adi akoina loin crystalline to be tabudabu real life ke crystal adi impurities yarkani defects yarkani aduna idealized crystal na ngasagi system amaki properties explain to we are aduna say impurities defects suma yarpada aduna ngasagi impurities kitang dang or body properties change to the way that a disorder is a kitang yardi to don't talk to me adu disorder is some hingalan god al karamba disorders in a percentage kaya or kanda ngasagi crystalline phase the gina amorphous phase natraga normal crystalline state the gina glassy phase kind okay siguma matanga nenas sinamu kariga mari lener ke matam ngasagi akoigi percolation edi kaina ngasagi akoina concrete ku maji lawrji concrete se da magi ahoba macha yawring khalone ahoba macha je kamai to ge ising khara hejin matam da mathak ta gine makhayo phawgidra ada ahoba mayam do karba kanda ahoba jina say for example centimeter cube da ngasagi bubble gumje taraga yawraje ada tadi ngasagi 1 meter tha ba concrete slab sida mathak ta ising hejin bakanda makha da phawgidra ꯍꯧꯔꯣꯏ ꯅꯠꯇ꯭ꯔꯥ ꯑꯗꯨꯗꯩ ꯉꯁꯥꯏꯒꯤ ꯕꯕꯜꯁꯤꯒꯤ ꯁꯥꯏꯖꯅ ꯀꯌꯥ ꯆꯥꯎꯔꯛꯄ ꯁꯦꯟꯇꯤꯃꯤꯇꯔ ꯀ꯭ꯌꯨꯕꯇ ꯀꯌꯥꯝ ꯌꯥꯎꯔꯛꯄ ꯑꯗꯨꯋꯥꯏ ꯀꯥꯟꯗ ꯉꯁꯥꯏꯒꯤ ꯃꯊꯛꯇ ꯍꯩꯖꯤꯟꯈꯤꯕ ꯏꯁꯤꯡ ꯃꯈꯥꯗ ꯇꯥꯔꯛꯀꯗꯒꯦ ꯍꯥꯏꯁꯦ ꯑꯗꯨꯒꯤꯗꯨꯁꯨ ꯐꯦꯖ ꯇ꯭ꯔꯥꯟꯖꯤꯁꯟ ꯃꯈꯜ ꯑꯃꯅꯦ ꯁꯤꯒꯨꯝꯕ ꯃꯌꯥꯝꯁꯤ ꯅꯩꯅꯕꯗꯨꯅ ꯉꯁꯥꯏꯒꯤ ꯗꯤꯁꯑꯣꯔꯗꯔ ꯄꯔꯀꯣꯂꯦꯁꯟ ꯀꯥꯏꯅ ꯇꯧꯔꯤꯁꯤ ꯌꯥꯔꯗ꯭ꯔꯥ
Any questions? Later, what can you know?
ꯑꯗꯨꯅ ꯑꯩ ꯃꯊꯪꯗ ꯂꯦꯅꯤꯟꯁꯨ ꯐꯦꯖ ꯇ꯭ꯔꯥꯟꯖꯤꯁꯟꯁ ꯑꯗꯨꯅ ꯐꯦꯖ ꯇ꯭ꯔꯥꯟꯖꯤꯁꯟꯁꯦ ꯌꯥꯝ ꯃꯔꯨ ꯑꯣꯏ ꯑꯗꯨꯅ